BC Calc, we're going over a review for our upcoming Chapter 7 quiz. Take a look at this tabular problem. We are told that g is an inverse function of f, and yet the table that we're given is only in regard to f. We're trying to write the equation of a tangent line. In other words, you know from the very beginning you're going to need to write in point-slope form. But you're going to have to find that tangent line slope of that inverse function for g, tangent line to g, at the value of x equals 2. That means we can say 2 comma something lies on g, and that means something comma 2 lies on f. Of course, we know that whenever you have the point a comma b lying on g, that means b comma a would lie on f, and vice versa. So I'm looking for 2 to show up for f, and I see 2 is showing up as a y value here at the point 3 comma 2. So I can say that 3 comma 2 lies on f, and that means that 2 comma 3 is going to be lying on g. So g prime of 2, as I take my derivative to get my tangent line slope, that's going to be 1 over f prime of 3. Remember that reciprocal relationship, and of course we're finding our tangent line slopes at different x values. Now f prime of 3, we actually are told right here, it's 2/3. So we could say 1 over 2/3. The reciprocal of 2/3 would simply be 3 over 2. That's the slope of your tangent line. That's your 3 over 2. We already saw that it's the point 2 comma 3 that lies on g. So as we clean this up, and as we try to work this all out, very nice and simply, the equation of our tangent line will be y minus 3 equals 3/2 times x minus 2. And that's your equation of your tangent line. As we come over to number 2, it's a very similar type of a problem. We know that we're going to have g is our inverse, and we're asked to find g prime of 2. So I know that 2 comma something lies on g, and that means something comma 2 lies on f. In other words, here's my f. I have my y value equaling 2, and it can be a little bit disconcerting, a little upsetting, as you try to find a solution at first. You'd think, wow, I don't have a table like I did earlier. I do know that my y value is a 2, and I'm looking for x. But try inspection. Maybe let x equal very simple values, like maybe 0. That wouldn't work. 0 to the 5th times 3 plus 0 minus 2, that won't equal 2. Maybe let x equal 1, and that does the trick. 3 times 1 to the 5th plus 1 minus 2. That's 4 minus 2. It is 2. So this is it. You'd have 1 comma 2 lies on f, and that means 2 comma 1 lies on g. So what we're going to do is quickly find that g prime of 2 is simply 1 over f prime of 1. Well, what is f prime? F prime, as we take our derivative, we'd get 15x to the 4th plus 1. And as I plug a 1 in, I think it's pretty quick to see that that thing is 16. My tangent line slope then, g prime of 2, is just 1 over 16. And we're done with problem number 2. As we take a look at number 3, definitely a problem that I think could be very upsetting. It's a problem that you could have done in the past, way earlier in the year, taking derivatives. And as we're doing that, there's a better way to deal with such problems, and that's through logarithmic differentiation. I'm going to take a log on the left side. In fact, I'm going to choose natural log. I'm going to take a log on the right side, and while I'm at it, I'm going to begin to start to break this down. The fourth root is really a 1/4 power, and we can just begin to see why this can be so helpful. You know, as I've got this log on the right-hand side, I can apply a property of logs where I can say, you know, just like we saw earlier in the chapter, natural log of m over n is the natural log of m minus the natural log of n. So this becomes the natural log of x squared minus 6 to the 4th minus the natural log of x plus 2 to the 3rd. I'm going to use my property of powers here, drop these powers down, and all of a sudden this problem becomes much, much nicer looking. I can now go ahead and take my derivatives. And the derivative on the left side, I'll get 1 over y and then a dy dx. Take my derivative on the right side. Well, the derivative of natural log is definitely always going to be 1 over whatever is inside that logarithm, whatever is inside of it. And then using this chain rule, the derivative of the inside will get a 2x. Likewise over here, I'm going to take my derivative, get 1 over x plus 2, and the derivative of the inside is just a 1. And I can begin to clean this up just a little bit. You can say, look, a 2 cancels this 4 and leaves me with a 2 here. And I'm going to continue writing all the way up here. I'm going to do a little cleaning up. I'm going to multiply both sides by y. And I'm going to have y. But now all of this stuff is going to clean up. I'll have an x up on top. Down below I've got my 2 and my x squared minus 6. And then I'll just bring the 3 over the x plus 2. And really we're almost done. What you can just realize is that that y was that very ugly expression of the 4th root of x squared minus 6 all over x plus 2 to the 3rd. And then I've got my remaining expression inside of these brackets. So definitely a preferred way to take this derivative in the sense that I didn't need the quotient rule. I didn't need to work with intense radicals. So we'll be making videos by page here. That wraps up page 1.